And welcome to 17.3, where we're going to be dealing with heat during changes of state. In this particular section, we're going to look at the freezing process, the melting process, boiling and condensing, and the amount of energy that is exchanged between the system and the surroundings during those processes. All right. So we're going to lead off by talking about the molar heat of fusion. Fusion. Of course, the term fusion means to bring together, just like you have nuclear fusion where different nuclei of atoms will come together. In this case, we're going to fuse or bring together different molecules. And so the sign for this, since we're dealing with enthalpy or heat, is going to be delta H, and we'll give it a sub FUS for fusion. And in this case, we're talking about the amount of energy, or the heat, absorbed by 1 mole of a solid substance as it melts into a liquid. All right. The reverse of that would be when you're actually going from a liquid back to a solid. It's called the heat of solidification, and we would give that a symbol of delta H solid. Now, as it turns out, those two processes or those two energies are exactly the same. In fact, I usually just refer to it as the heat of fusion even when it's going from a liquid back to a solid, because it is the same amount of energy. It's just that the energy is going in an opposite direction. Here's what we mean. As you go from, say, water as ice or H2O as ice to the liquid form, this process is endothermic. You have to absorb energy, or the ice has to absorb energy to melt, and it absorbs, or the delta H of fusion would be a positive 6.01 kilojoules per mole. That is, for every 1 mole of ice, it has to absorb 6.01 kilojoules to melt it. Now, the flip side of that, if you were to take liquid water, H2O, at 0 degrees Celsius and freeze it, the delta H of solidification would be the exact same value of 6.01 kilojoules per mole. But in this case, it'd be negative. It's actually exothermic. Why? Because the water has to release heat or lose heat in order to freeze. So the way it turns out is that they're the exact same numbers, just in the opposite direction. So some people would just simply say that the delta H of fusion, or the heat of fusion, is going to be equal to the opposite of the delta H of solidification. But typically this is the one that we deal with. You just got to realize that it's endothermic as it melts, and it's exothermic as it freezes. Alright, so let's go ahead and take a look at this. It says how many grams of ice at 0 degrees Celsius will melt if 2.25 kilojoules of heat are added. So as always, you start by writing down what's given, 2.25 kilojoules of heat. And you want to take that into grams. How many grams? Well, we know how to go from kilojoules to mole. Alright, so 1 mole is going to need 6.01 kilojoules. So now the kilojoules divide out. You're in moles. They want grams, so you got to go from moles to grams, which is using the molar mass. The molar mass of water is 18.02 grams per mole. Just add them up. The moles divide out. And now if you take your 2.25 divided by 6.01 times 18.02, looks like 6.75 grams of ice will melt if you add 225 kilojoules of energy to it. How many kilojoules of heat are required to melt a 10-gram popsicle at 0 degrees Celsius? So now they want us to figure out how much heat is necessary. Well, again, you're starting with 10 grams of popsicle, which is just ice. We're going to assume that we don't have to worry about the flavorings in the dye or anything else. So this is just the popsicle. the ice itself. So the first thing we have to do is change this into moles, as we typically do. 1 mole of ice has a mass of 18.02 grams, so that'll get us into moles. And to change that into the energy, it's 6.01 kilojoules over 1 mole. The moles divide out, we're left with kilojoules, and so we have 10 divided by 18.02 times 6.01, and we get 3.34 kilojoules of heat that would be required to melt a 10-gram popsicle. All right. Now going to the other end, how do we get this thing into the gaseous phase? Well, you have to add heat to get it into the gaseous state, and we call that the heat of vaporization. And we give it a symbol delta H, the energy change or the enthalpy change, as you vaporize something. All right. So this is the energy or the amount of heat necessary to vaporize 1 mole of a given liquid. And that's going to be the opposite of the molar heat of condensation, which we would say is delta H COND for condensation. And so if you look at the reaction or the vaporization of water into steam, this particular process is going to be requiring 40.7 kilojoules per mole. So we would call that delta H of vaporization is going to equal that value. Or then the opposite, if you're going to condense steam back into water, you're going to have to remove heat from it to get it back into the liquid phase, and it's going to require that you remove 40.7 kilojoules per mole of steam. So once again, they're opposite processes. Here's a bunch of different values for the heats of fusion and heats of vaporization, and notice that they do record them as heats of fusion and vaporization. I typically don't see tables of heats of condensation or heats of solidification unless you have a particular application that always uses that. Typically, we're going to report it as heats of fusion and heats of vaporization. All right. So let's go ahead and try this. How much heat in kilojoules is absorbed when 24.8 grams of water at 100 degrees Celsius and 101.3 kilopascals is converted to steam? So if you have your 24.8 grams of water, of course, change it into moles. Everything is done in moles. So 1 mole of water has a mass of 18.02 grams. The grams of water divide out. We're left with moles. They want to know what the heat is when you convert it into steam. So let's go ahead and take a look at the heat of vaporization. Again, it's 40.7 kilojoules per mole. Per 1 mole. And so if you perform that calculation, 24.8 divided by 18.02 times 40.7, we got 56.0 kilojoules of heat would be required to vaporize 24.8 grams of water at 100 degrees Celsius. All right. Now, for those who are following this without much problem, there's a more advanced problem where you can analyze or you can take a look at a system that is going through multiple phase changes. For example, you could start off with, say, ice below 0 degrees Celsius. You can warm that ice up. Now that's going to require, let's do this over here, that's going to require that you use the Q equals SM delta T equation for ice, using ice, the specific heat for ice. Then you're going to melt the ice at a constant temperature, using the mathematics that we just used. Then you're going to raise that temperature of the water up to the boiling point by using, again, Q equals SM delta T, where you have to use the specific heat of water, which is different than the specific heat of ice. Then you're going to use your heat or enthalpy of vaporization to boil the water off. And then you will use, once again, Q equals SM delta T to raise the temperature of the steam, but of course the specific heat of the steam is different than that for the specific heat of water, liquid, and ice. So for those who are inclined, you can take a look at this next problem. We'll handle it in the next podcast. See you next time.